Okay, welcome to Stage 2 Physics. The first topic we're going to look at this year is motion and relativity, and the first subtopic we're going to look at is projectile motion. And in part A, I'm just going to explain a little bit about what we mean by projectile motion, and then in part B, we'll look at how we do calculations about projectile motion, and we'll finish in the third video looking at the effect of air resistance on projectile motion. Let's get into it. Okay, let's just start by talking a little bit about the structure of these notes. What you'll see in all of these, up in normally the top left-hand corner, usually hopefully in green text, is the science understanding from the SACE curriculum outline. So this is what SACE says that you need to know and what you need to be able to do. And we use this as a checklist to inform the notes that are on this side. It is also, when we write a test, we need to make sure that the test is addressing only things that are here. The exam, when the exam's set, everything will relate to the points that are here in this left-hand column. So this can become a really good checklist as you go through, that you can read these through and check, yep, I understand that, yep, I need to know how to do that. So what are we looking at in this first part? Uniformly accelerated motion is described in terms of relationships between measurable scalar and vector quantities, including displacement, speed, velocity, and acceleration. So we're going to talk about what scalar and vector quantities and what distance, displacement, speed, velocity, and acceleration is. And hopefully, for most of you, that's revision of what you did last year or even in year 10 or earlier. We're also going to look at the motion under constant acceleration can be described quantitatively. So quantitatively means with numbers, using the following formula. So these, if you like, what we'd normally call the equations of motion, we'll just briefly talk about them and we'll get more into those in the next couple of slides. So firstly, a scalar is a quantity that has a size but not a direction. So we can think about something like our mass. Our mass doesn't have a direction. We weigh, 74 kilograms, it doesn't have a direction. A vector is a quantity that has a size and a direction. And we can think of force. A force can have both a size, we can have a small force or a large force, and that force always acts in a direction, whether it's up, down, left, right, it's always a direction. So that means that it is a vector. So distance is a measure of how far an object travels. If we go from one point to another, let's say we're going from here to here and we take this path here, that path, the length of that path represents the distance covered. Displacement is a measurement of the change of position of an object, and it has a size and a direction. So if we follow this path, our displacement is only the shortest distance between where we started and where we finished, and this has a direction. Direction of this arrow, the direction is important. So that would be roughly southeast if we used the compass type directions. Speed is the rate of change of distance. So whenever we see rate of, we think in terms of time. How fast or how slow, how quickly or how slowly are we covering distance, and that's what our speed represents. Velocity is the rate of change of displacement. So velocity is equal to S is displacement divided by time. I really should actually add that into this graph that I haven't put that there. I do have that when we get down here. Displacement S measured in meters. And acceleration is the rate of change of velocity. So again, velocity was our displacement divided by time, how quickly or slow that's happening. Acceleration is our velocity divided time. If we have a fast acceleration, we either have a large change in velocity or it happens over a very, very small time, making the acceleration larger. So that is the distance, displacement, speed, velocity, and acceleration. I want you to think for a sec. Distance, is that a scalar or a vector? So is direction important? Well, no, not for distance, but yes, it is for displacement, so that's a vector. Speed is related to distance, so that's a scalar. Velocity is a vector because it relates to displacement, which is a vector. Acceleration relates to velocity, in terms of these formulas, and velocity is a vector, so that's a vector. We also think of acceleration through Newton's second law. The acceleration of an object is proportional to the force, inversely proportional to the mass. So because it's related to the force and the force is in vector, that is also a vector. So next we get into these equations of motion under constant acceleration, we might call them. These equations here, hopefully you've seen some of these before. You might have only looked at these in one dimension, whereas this year we're going to look in 2 dimensions. We'll talk about what that means as we go on. But I know some of you did some 2-dimension stuff previously, so you may have seen this before as well in 2 dimensions. These equations are given to us on the formula sheet, so we don't actually need to remember these formula. We just need to be able to, if you like, remember how to use them. So V is our velocity, and you may have seen this written previously as final velocity. It could indicate the final velocity or the velocity at a particular time. So velocity at a particular time. V0 is the initial velocity. Velocity is measured in meters per second. And I'm just looking at this, when that's saved, because I swear that was there, these should all have a little minus sign in front of them. So I'm not sure what's happened to that when I've saved them as a PDF. But meters per second, ms to the minus 1, or acceleration down here, ms to the minus 2 meters per second per second. If you're not sure about this -1 notation, it's basically scientific notation. Please ask and I'll explain that to you, how that means exactly the same thing as m/s. I'm hoping by year 12 you've seen that sort of scientific notation before. But if you don't know about it, ask, because it's not that complex and it's definitely worth understanding. So we have 3 equations that we commonly use. This first equation, which allows us to work out the final velocity if we know the initial velocity, the acceleration, and the time. So the classic, if we drop something and it's accelerating, if we know how long it fell for, we can work out its velocity. We have this formula here for working out the displacement of an accelerating object, which starts out, if you like, a bit like the normal displacement for a constant velocity problem. Displacement equals velocity times time. And then we add this factor here that takes into account the acceleration. And then we have this third formula for working out the final velocity if we know the initial velocity and the displacement rather than the time. So this is the classic, if you drop something off a cliff and you know how far the displacement, how far it's fallen, then you can work out the velocity. Whereas this one we can work out based on time. So they are the 3 equations of motion that we're going to use, and we'll explain shortly how we're going to use those. So just before we do that, let's just think about exactly what we mean by projectile motion. And this diagram here represents launching a projectile, throwing it into the air. Obviously it will go up, it'll reach a maximum, and then it will come down on the other side. And we're looking here at what we call in the absence of air resistance. So there's no effective air resistance. We'll talk about that in the final part of this topic. So projectile motion can be analysed quantitatively, so with numbers, by treating the horizontal and vertical components of the motion independently. So if we take our velocity, and I think I might draw over this diagram, and we have the velocity represented by that line there, we can, or it could be the velocity, or it could also actually be the displacement, we can break that up into the horizontal component, VH, and the vertical component, VV. And we'll get into the next point here. If we're talking here about velocity, the vertical component is equal to VV equals V sine theta. So if we take the velocity, times it by sine theta, and in this case, theta is that angle in there. That'll tell us what the vertical component is. The horizontal component is equal to V cos theta. I'm assuming here that you're comfortable with right-hand trig, and in a minute with Pythagoras and that sort of thing. So, if we know the velocity at any point, we can work out the horizontal and vertical components, and that helps us analyse the motion, which is what we're going to do soon. So we'll see that in a minute. In terms of this first dot point, I guess we've sort of jumped into the second. Construct, identify and label displacement, velocity and acceleration vectors. Let's say if we were talking about the displacement in this sort of first part of the journey here. So let's use blue for displacement. That there would represent the displacement. And then obviously we could break that displacement up into the horizontal component of the displacement, if we wanted to, and the vertical component of the displacement. So horizontal, how far across the ground has this projectile travelled? Vertically, how high has it gone? Now, we can also consider for this projectile the velocity. And in this case, the velocity vector is just in the direction, which is, if you like, at a tangent to the line that it's travelling at any point. So say that's V there, and then this will look very much like what I just did before. We'd come across here, and that would give us our horizontal component, which we could obviously work out with this formula down here, and then we could get the vertical component there. And we could, for any of these points, if you like, look at the velocity vector. Note the displacement vector goes from where it started to where it finished, whereas this one doesn't go straight to the next point because it goes, I know it's a bit hard to see, but it goes at a tangent to that grey line that you can just see in the background. If we wanted to look at the velocity vector, say at this point here, that would be basically going down there along like that. And again, if we wanted to, we could break that into the, oops, wrong colour. We could break that down into the, oh, sorry, I went too far there. Redo. We could break that down into the horizontal component there and the vertical component there. I won't do this for every point. So that should be a V and it should be a VH. So that's the velocity vector. And then also in each case, we would have the acceleration vector. I'm just going to pause for a sec and think about what would be the direction of the acceleration of this projectile during its motion. Okay, hopefully you know that gravity only acts downward, so gravity only acts in a vertical direction. So what we can see here is the horizontal component of the velocity. The horizontal there doesn't change. What changes is the vertical. Here it's going up, and then it's changed to coming down due to gravity here. So gravity always acts downwards, and gravity is also constant. I won't draw into that second dot because that'll get a bit confusing. So yeah, that there is representing the acceleration due to gravity. So that's always downwards back towards the centre of the earth, and that's always constant. The next thing that we need to know how to do, solve problems using the constant acceleration formula. That was the first formula, acceleration equals Vf minus Vi on t. Let me just quickly write that down. I think that's pretty straightforward here, and I suspect that you've all done problems, whether we write it in the form V, I would, in year 10, year 11, write Vf minus Vi over t. This year we'd use more the notation V equals V0. I'm going to roll here with a pen tonight. V minus V0 over t. Or you might see even delta V over t. Delta being the change in velocity, so the final minus the initial. I'm hoping you can all sort of work out acceleration, and you've done that probably back as early as year 10 or even earlier, hopefully. So the next thing, and we're going to cover those sort of more calculations more in the next video. The next thing, use vector addition and trigonometric calculations to determine the magnitude and direction of the velocity of the projectile at any moment. So it's the opposite here. Before we talked about how we could resolve it into the two components. Now we're talking about if we know the horizontal and the vertical, how do we put them back together to get the total velocity? And basically we do that by using Pythagoras Theorem. So what colour should we go? Black. So if we want to combine, we would go that, sorry, I just got something come up that I didn't want. V would equal the square root, because it's a right angled triangle, of VH squared plus VV squared. And if we wanted to work out the direction, basically because we knew VH and VV, we could go tan theta equals, basically we know tan is opposite over adjacent, hopefully. So that would be V over VH. Or we could use sine or cosine if we knew sine is equal to, sine theta is equal to opposite over hypotenuse. That would equal V over V. And we could use cosine as well, but I won't go through that. So when we want to go back the opposite way, we can basically, so if we know the horizontal and the vertical, we can use these things here in black to work out the both magnitude through the magnitude here, velocity with Pythag, and then we can work out the direction using trigonometry. So I will do an example calculation in the next video, which will probably demonstrate those skills. But again, I'm hoping if you're doing year 12 physics that when you look at that bit of maths, you go, yep, I could easily add those two things together and work out the total velocity. So just before we finish, let's just think a little bit more about how the gravity or the gravitational force affects the motion of objects near the surface of the Earth. So firstly, gravity is a force, it's a constant force, so therefore causes things to undergo constant or uniform acceleration. And what we see is because it only acts in a vertical direction, gravity only affects the vertical velocity. So hopefully you've already watched this Monkey and the Hunter classroom demonstration. It really is a really good demonstration of that idea that gravity only acts in a vertical direction. But this diagram I think also shows it really well. If we imagine we had two balls and one of them, say, rolled off a table with some speed this way and the other one was just dropped at the same point, what we would see is firstly, or let's think about the horizontal first. This ball that gets rolled off the table, its horizontal velocity would be constant. So each of these dots basically represents where the ball is at a fixed time interval. So, you know, this might be at 0.1 second after it, or 0.1 second after it left, 0.2 seconds, 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1 second after it rolled off the table. And you can see horizontally, the displacement is the same in each case because there's no force acting in the horizontal direction. So the horizontal component of the velocity stays constant. However, vertically, there is an acceleration. So you can see in the first little part, well, this first dot's almost blurred into this dot. But if you look at this second dot here, you can see in both cases it's fallen the same distance vertically. So the vertical displacement, the down displacement is the same. Same here, same here, same here, same here. So what that means is that we can consider the vertical component and the horizontal component separately. The horizontal component doesn't change, it's constant, so it's like a constant velocity problem. The vertical changes due to acceleration, so we use those formulas for motion under constant acceleration that I introduced a couple of slides ago. This second SACE science understanding from the SACE curriculum I've actually pulled out from further on, but I think it's probably easier to just talk about now. What this represents is a multiple image representation of a projectile. So by multiple image representation, we mean where is the projectile at a certain fixed time interval. So as I said before, this is where it is after a certain time. After this, the idea that the time intervals between these dots is constant. So we're showing where it would be at a certain time. Back when I went to school, we used to go into a dark room and we used to have projectiles and we had a flash, like a strobe light that would flash at a constant time rate, and you would take a photograph with the old film camera and you would drop something and you would see where it was at certain intervals. Well, theoretically, you would only see where it was when the light flashed on, and those light would flash on at a constant time. Then you would send off the photo to the place where you used to get photos processed, which you kids probably have never even heard of these days. And then 2 weeks later, you would get the photos back and they wouldn't have worked anyway, and the teacher would say, here's one that's what it should look like, and you'd analyse that anyway. You can do this now using an app called Motion Shot. If you want to play around and develop multiple image photos, by all means get the Motion Shot app and have a go at it. If we get a chance one day, I might even show that to you in class, but it's probably not worth spending too much time on. As I said before, the best demo of what's happening with this vertical and horizontal motion due to gravity is this monkey and hunter classroom demonstration, which I've given you a link to here. I have built one of these before. They do work, but they're very temperamental, and it's probably not worth wasting the time on in the sort of learning environment that we have now. Okay, that's it for this video. In the next video, we'll get into looking in detail at some calculations. Cheers.